Ordinary Simple Annuities, Unit 10, Part 4, the last of our 4-part series. Here we're going to wrap it all up with solving for the others, all that kind of extra dangling remainder stuff that's part of this general unit, including finding the term of the annuity, finding the interest rate for the annuity, working with the effective rate of interest, which is a little bit different than the interest rate that we find when we use our calculator to find the interest rate, and set the groundwork for general annuities, ordinary general annuities. So similar kind of thinking when we were talking about payments, and we rearranged the future value formula, future value for an annuity formula to find payment. Same kind of idea here. The trick being, of course, n, as we can see looking at the formula for future value, is an exponent. But that's not a problem. A little bit of trickiness, but not a problem. Right? We can use a natural logarithm operator to pull down that exponent. Very powerful, very useful mathematical tool to find the value of an exponent when the value of that exponent is unknown. And so we rearrange, and we've got some natural logarithm operators in both the numerator and in the denominator. Now, we remember back from our good old high school days, and we remember that negative numbers, you can't find the natural logarithm of a negative number. It doesn't exist. So typically, when we're solving for n, we just have to be aware that the future value and the payment are going to have the same sign. It's both positive, both negative, whatever the case may be. Typically, they'll have the same sign. Also, what throws this into kind of a loop is the sort of the current age of interest rates is somewhat unique in that you have some European bonds, some Japanese bonds trading at negative interest rates, and that really kind of throws this formula for a loop as well, because it introduces a negative number in there, and if future value and payment have the same sign and you have a negative interest rate, it complicates things. So this wouldn't be necessarily the best tool in that regard. Luckily, for a first-year class, we don't have to worry about those sort of more complicated, complex issues, but something to kind of neat to think about nevertheless. So finding the periodic rate of interest, no formula for this because there's no formula. It's just there isn't one. Right? And some things are like this. Even your calculator doesn't use a formula to find the interest rate. It actually does it trial and error. It just does it so extremely fast that we don't notice that it's doing a whole bunch of trial and error calculations, but it is. I remember my very first financial calculator. This would be in the late 80s. And when you could solve for a periodic, you'd solve for the interest rate, and you could go and grab a coffee, daydream, look at the ceiling, gawk around, because it was chugging, it was working hard, and there was a noticeable lag between you clicking solve I and an answer coming out. Now, boom, you don't even notice that there's been a bunch of essentially trial and error calculations going on. Okay. So that one, even if you are the most anti-calculator person in the world, you are stuck using a calculator to find I. All right, let's do some questions. Question 1, what payment is required? So we're asking us for the amount of the payment. Is required at the end of each month for 12 years to repay a $197,000 mortgage if interest is 3.35% compounded monthly. So regular payment intervals at the end of a regular time period or period interval, we have an annuity. So we start thinking all our basic values for that annuity: n, interest rate, present value, payment, which is what we want, that's what we're looking for, future value, how many payments in a year, how many compoundings in a year. So all our standard stuff right now. It notes that we will pay at the end of each month for 12 years, 12 months per year, times by 12 years. 144 months in total. Interest rate is 3.35% compounded monthly. So C over Y is 12. Present value, that's the amount of the mortgage. Now that's a positive because that was money that came to us to buy whatever it is that we were buying here. Okay, so money coming towards us. Payment's what we're looking for. Future value, any lump sum payment owing at the end, doesn't appear to be. And lender hopes that we paid it all off. And what was that payment frequency? It is payment required at the end of each month. So we know that there's 12 of those every month. Okay. So now, similar to what we were doing before, right? We enter all those things into our respective calculator and we solve for payment. It's really no different than what we were doing before. And so at the end of it, we'll get 1663.29. And so when you report that, we just report it as the payment. Sometimes it may come out as a negative or a positive, and really the negative positive stuff is relative. If you're receiving it, it's a positive to you, right? To the lender, $197,000 went away from them. That would be a negative number to them, and then the payments are positive. Whereas if you're the borrower, it's the reverse. So the whole idea of positive, negative, we use it for the calculations, but it's really relative. So when you report the answer, we would just say that the payment is $1,663.29. I wouldn't get too wrapped up in the positive, negative part. Okay. Question number 2. This is a really interesting question here, and this is a very applied question because this is a question, an issue that most people face. You have a period of saving and you have a period of expenditures. Right? That's sort of classic lifestyle modeling if you're an economist, in that you spend some time saving money and then when you retire you spend the money. Now here it's a slightly different situation, but the same kind of idea. So we're starting 3 months after their daughter's Megan's birth. Her parents made deposits of $120 into a trust fund every 3 months until she was 21 years old. Okay, so a process of saving. The trust fund provides for equal withdrawals at the end of each quarter for 4 years, beginning 3 months after the last deposit. If interest is 6.75% compounded quarterly, how much will Megan receive every 3 months? Okay, so again, two annuities here, right? Remember, annuity equal payments, equal periods for those payments. Now, here we have equal periods throughout. However, the payment amount changes. So totally different annuity. So we draw this thing up. And timeline is kind of always nice. When in doubt, draw the timeline. And so on a period of 0, 21, doesn't need to necessarily be the scale, and mine certainly isn't. And then to 25. First segment is we have the saving part, right? Second segment, we have the spending part. And again, classic problem, Save throughout your lifetime, spend through your retirement. Same kind of idea here, okay? Some folks do this where they save so much for their kid, and then maybe at 18 this comes out, and the idea is to supplement earnings while the child won't be a child any longer, but while their kid is in the university or something like that. Okay, so let's look at that saving annuity first, and we know it's annuity, equal payments, $120 every quarter, and so we'll chart that out all the way through. We have our payments per year, and we have our compoundings per year. Okay. Same story with the spending, right? We're going to spend for so long. We're going to have our I. We're going to have our PV. We're going to have our payment. We're going to have our future value. Won't be much in that case. And the P over Y and C over Y. Okay. So let's sketch this out and with the information that we have. Okay. They are going to be connected. So Sometimes you find one annuity then the other. Sometimes you find the other annuity and then you work backwards. We don't know yet. It depends on exactly what the question wants us to do. So saving, we're going to save for 21 years, 4 periods per year. So 84 payments go into the trust fund. Interest rate is 6.75%. It's compounded quarterly. The payments are also quarterly. Next thing, present value. Do we start off with any big lump sum payment? Nothing mentioned. So let's go with 0. The payment is minus 120. And future value, we don't know. Okay, that's what we're trying to determine. The future value gives us how much money has accumulated when Megan turns 21. Now, when she turns 21, then she gets to pull money out of the trust fund. So the money she starts with in the trust fund is the same amount as what ends up with from the savings plan. Right? There's the connection between the two annuities. Right? The amount of money that Megan starts off with when she starts the withdrawal is the same amount as what ends up with at the end of the saving part of this plan. She will spend for 16 periods, right? So end of each quarter for 4 years, so 4 times 4. Nothing to suggest that the interest rate has changed or the compounding has changed. And the periods, it's still quarterly. She still gets quarterly payments. Okay. Payment, this is what we need. And future value, we're assuming that Megan spends all the money from this trust fund. Okay. So in the second annuity, the spending annuity has 2 unknowns. Okay, so that clearly isn't going to be where we start. The saving annuity, however, has just one thing we need to determine, and that is the future value. So we determine the future value, and you plug it into your calculator, and you can pause and then resume. Okay, and future value is we get $21,889.92. Okay. That becomes the present value. So we reinvest that money into the second annuity. Okay? Now, we're buying annuities, so technically it becomes a negative number, although not going to be a big deal in this question. Okay. And then we work through the second annuity now and see how much does she get to spend every quarter, or how much money does she receive every quarter. Okay, so try that. You can pause if you like. Pause me talking, by the way. And now, when we spit it out, we get the $1,572 and around 56 cents. I rounded a little bit. Okay. So the key thing is we have a saving part, a spending part. They're connected to each other. A very common problem. I love this kind of problem. This is a great problem because we've got a lot of moving parts, but it's so wonderfully realistic. Anyway, thank you for listening. And now let's move on with the rest of the show. Okay. Question number 3. So question number 3, Rand borrowed $35,000 and some change to buy a new Honda Accord. Payments were $553 per month for 4 years. What is the nominal interest rate for this loan? Assume that the nominal interest rate is compounded monthly. Okay, so we need that little compounding hint. Otherwise, it becomes a little trickier to solve. Okay, so regular payment, right? Payment $553 per month. So payment interval is constant. Payment amount is constant. We got ourselves an annuity, folks. Okay, so NI, present value, payment. I should get a stamp that has this on there. Payments per year, compoundings per year. And how many payments do we make? Well, we do this for 4 years, every month. 4 times 12, 48. Interest rate, we don't know. That's what we want to find. But we do know it's compounded monthly, so compounding period is 12. Present value, how much did we borrow? $35,476. It's positive because there's money flowing to us, right, to buy the car. Payments, money flowing away from us back to pay for the borrowing, negative 553. No lump sum at the end of this thing, and the lender is hoping that we have it all paid off, and we're making 12 of those payments per year. Okay, so now we roll through, we solve for I. Okay. Go through the process, and we see that I is 13.53. Now, technically, to be correct, we would say that I is 13.53% compounded monthly. Because it is asking for a nominal interest rate, you report the number, but you have to also include the compounding period. That is very important. There's two components to a nominal interest rate. There's the interest rate itself, and there's also the compounding frequency. They're both important. Okay. So we're all set there. Now, one last thing to talk about, and that is the effective annual rate. So the effective rate of interest. Now, effective rates of interest are the equivalent rates of interest compounded annually. And there is a formula for effective, so F is equal to 1 plus I to the M, or if we remember from way back in our Unit 9 compound interest days, it's just the number of compoundings per year, and minus 1. Okay. Now, and that formula is fairly easy to use. I'll show you how to do it on the calculator as well. In Alberta, you will see the effective rate of interest in every consumer loan contract. It's often called APR. So when you see advertisements for car loans especially, you'll see this APR. That is essentially, it stands for annual percentage rate, but it is essentially the effective rate of interest. It allows us to compare different interest rates, because sometimes 13.53% compounded monthly is worse if you're borrowing than, let's say, 13.53% compounded semi-annually, right? Remembering the more frequent compoundings, the more often every year we convert interest to principal, is great for the lender, not so great for the borrower, right? Hence why it's nice to look at that APR, or effective rate of interest, and so that we can then compare without this compounding sort of muddying things up a little bit. So let's do some examples of this. So let's take some previous interest rates that we had, right? And let's say we had an interest rate in the previous question of 6.75%, with those compounding periods, number of compounding periods were quarterly. Okay? So how would I tackle that particular issue? Okay, so we roll back to our tails of the interest of the calculators again. Okay, turn these guys on, and so for on the TI-8084, we would go back up to apps, right, and then finance, but we wouldn't do TVM solver anymore. We'll scroll. I'm going to scroll up because I know where EFF is, but you could scroll down and hunt for it as well. So we scroll up and we go up to EFF. It's C, just above our good old friend days between dates. Okay, so I go up to EFF, effective rate of interest. I push enter. Now I get this thing with a bracket. Now, first argument in this is the nominal rate, 6.75. Okay. Nominal rate just as we read it. Okay. The second argument is the number of compounding periods. So I got to remember to put the comma. So I check comma, number of compounding periods, and in this case was 4, and I go with 4. Close that bracket, push enter. Okay. And when I look at that, I see that the answer is 6.9, roughly 6.923%. Okay. Now, let's roll over to the BA2 Plus, and we'll turn this thing on. Now the BA2 plus is slightly different. You see above the number 2, the conv, interest conversion. So I'm going to go second and then the number 2. And you'll see comes up nominal. Okay, so let's put in the 6.75. And I push the enter, the top left. Okay, push enter. The little equal sign comes up. This is very good, means it's in the register. Now I'm going to scroll up. Compounding periods, not 12, it's 4. So I push in 4 and then enter again. Right? Equal to sign comes up. I go up one more time. Now we see EFF. Now that is not the effective interest rate. We've got one more step to go. We've got to push the little compute button. Right? Push compute and boom, same answer comes up. 6.92, roughly 923. Okay, and there's the effective annual rate for this particular interest rate. Okay, so if it was compounded annually, that's what it would be compounded annually as. Right? So if we have a variety of interest rates with a variety of compoundings, we can then find the effective annual rate for each one of those, and then that'll give us some guidance as to interest rates that are either better or worse depending on the situation. Okay. So we're transitioning into ordinary general annuities, which are coming up. Same principles as we had with the simple annuities, except now the number of payments per year is different than the number of compoundings per year. And in order to preserve your sanity, we'll change the P over Y first, then change the C over Y. We've noticed so far in our experience that whenever we've changed the P over Y, the C over Y automatically changes. Luckily, when we change the C over Y, the P over Y does not change. So we just have to be very careful that we change the P over Y first, then change the C over Y. That's very, very important, so that if you forget to do that in that proper order, you'll get answers that are oh so close, but just a little bit out. Very frustrating. Okay, so again, just to wrap it all up, ordinary simple annuities, 2 big conditions. Payments are made at the end of the interest conversion period, with the first payment at the end of the first interval, hence the ordinary part. Payment period and interval, payment period interval and interest conversion are equal, hence the word simple. Number of payments can be solved using formulas, much easier to do it on the calculator. However, interest rate calculations strictly relegated to using calculators for that one. Okay. Now we'll relax the payment period, interval, and interest conversion being the same. Hence, the simple is going to disappear, and we're going to go to general. General is kind of like just means, hey, it works all the time. So if it happens to be the same, the formulas for the general annuity will still work. Hence the word general. Okay. Anyway, thank you very much. Stay tuned. More annuities are coming up.